What is the limitation of the TCP socket's basic communication model?
The basic TCP socket communication model is simple and can only support one-on-one communication. It uses synchronous blocking, which means that while the server is handling the network I/O of one client, if there is a blocking read/write operation, other clients cannot connect to the server.
How can the server support multiple clients without wasting resources?
To support multiple clients, one way is to use the multi-process model. In such model, each client is assigned a separate process to handle their requests.
How does the multi-process model work?
In the multi-process model, the main server process listens for client connections. When a connection is established, the accept function returns a connected socket. The server then forks a child process, creating a copy of the parent process's resources. The child process can use the connected socket to communicate with the client, while the parent process continues to listen for new connections.
What are the limitations of the multi-process model?
The multi-process model can handle a limited number of clients. Creating a new process for each client consumes system resources, and the context switching between processes incurs performance overhead. As the number of clients increases, the system becomes less capable of handling the load.
How can the performance be improved compared to the multi-process model?
To address the limitations of the multi-process model, we can use the multi-threading model. Threads are lighter than processes and can share certain resources within the same process, reducing the overhead of context switching.
How does the multi-threading model work?
In the multi-threading model, when a TCP connection is established between the server and a client, a new thread is created using the thread_create function. The connected socket's file descriptor is passed to the thread function, allowing communication with the client. Multiple threads can be created in advance and stored in a thread pool. When a new connection arrives, the socket is added to a queue, and the threads in the pool handle the connections by retrieving sockets from the queue.
What is the advantage of using a thread pool?
Using a thread pool avoids the frequent creation and destruction of threads. Instead of allocating a new thread for each connection, existing threads from the pool are utilized. The thread pool maintains a global queue, and threads lock the queue before accessing it to avoid thread concurrency issues.
What is the limitation of the multi-threading model?
While the multi-threading model improves performance compared to the multi-process model, there is still a limitation. If each new TCP connection requires the allocation of a new thread, maintaining a server that can handle tens of thousands of connections, C10K problem, would be impractical. The system would be overwhelmed by the overhead of managing a large number of threads. A technique called multiplexing is used to improve the situation.
What is multiplexing and what does it provide?
The term multiplexing refers to the ability to combine multiple requests or events into a single entity or stream, allowing them to share system resources and be efficiently processed. In the context of I/O, multiplexing involves consolidating multiple socket connections or requests into a single process or thread, enabling them to be handled concurrently or in a time division manner. Therefore, there is no need for separate processes or threads for each connection or request. This enables efficient resource utilization and allows for better scalability and responsiveness in handling multiple I/O operations.
How is the consolidation achieved in multiplexing?
The consolidation is achieved by using techniques such as select/poll/epl system calls that allow a process or thread to monitor multiple socket connections or requests simultaneously.